Welcome. In this course, you will learn some of the basics of artificial intelligence, and you will learn about one of the most popular implementations of artificial intelligence, the neural network. You'll also build a simple neural network from scratch using Python and train it to make predictions. The goal of artificial intelligence is to make predictions given a set of conditions. This is actually easier than it might sound. If you ask me the sum of 2 and 2 and I tell you it's 5, that's a prediction. Now, it's an inaccurate prediction. The correct answer, of course, and correct prediction would be 4. So a better goal might be to make predictions that mimic human response. And notice that I said human response, not human intelligence, because there are many ways to predict the sum of 2 and 2. One of them is a set of conditional statements. Take a look at this short Python script that would predict the sum of 2 numbers. Obviously, this is not the most efficient way to add 2 numbers, but if the range of the numbers is 0 to 2 inclusive, it'll work. However, essentially artificial intelligence is about discovering rules that will make predictions to mimic human response, and this set of conditionals will describe rules to add 2 numbers. Now, a better approach might be to use machine learning or even deep learning. In the script that you just saw, the rules are hard-coded using Python statements, and as you can imagine, being thorough using this tactic would be a challenge. Therefore, with machine learning and deep learning, you'll provide representative examples of what you want to predict. So you would show a machine learning algorithm sums of many different pairs of numbers. The algorithm would analyze them for commonalities and eventually discover the rules to be able to predict the sum of any 2 numbers. The result of analyzing the examples or training data is a model. So we could say that the goal of machine learning is to train a model that will make predictions to mimic human response without being explicitly programmed. Here's a diagram that explains the process. First, you start off with the training data, again the examples. Then the machine learning algorithm trains the model based on the training data. After that, you use the model to make new predictions based on data that was not used during the training process. This is important. The model should be able to make accurate predictions on data it has not seen. One problem that arises in machine learning is how to represent data. Computers like numbers, and it's often necessary to convert data into numbers so that a computer can process it. Take, for example, text data, such as the sentence, "Dave watched as the forest burned up on the hill." 2 of these words, watched and burned, are inflected forms. For example, the base form of watched is watch. Reducing an inflected form to the base is called lemmatization and is a common task in natural language processing. After you apply lemmatization to the sentence, you can take the number of times each word appears in the sentence. And these frequency counts will convert the text to numeric features using what's called a bag of words model. This process, called feature engineering, is a common task in machine learning. You may have heard about deep learning, since it's a hot topic in AI right now. Deep learning applies neural networks to machine learning and automates feature engineering. As deep learning deals with more complex data such as images, automating the feature engineering process improves the performance and accuracy of models. In the next lesson, you'll begin to learn about neural networks. As mentioned previously, neural networks are used in deep learning. The structure of a neural network arranges the values that it uses to train the model into layers. Each layer will manipulate the training data and forward the output to the next layer. And at the end, the output is a prediction. In this way, you can consider each layer to be a step in the feature engineering process. To train a neural network, you first take an example from the training dataset. The layers of the neural network manipulate the example and make a prediction. Then it compares the prediction to the observed values in the training data. Based on how good the prediction was, the values, called weights, in the layers are adjusted to make better predictions in the future. This process is repeated over and over for each example in the training data. Implementing a neural network, which you'll start in the next lesson, requires doing lots of operations with vectors. A vector is basically a multidimensional array, or an ND array in NumPy. Specifically, vectors support the dot product that is used to determine the similarity of two vectors, and the similarity is used to make predictions. Another important task in neural networks is linear regression. It is used to model the relationship between dependent variables and two or more independent variables. This can express the dependent variable as a weighted sum of the independent variables. For example, if you have a data set with the price of houses, their age, their location, and other variables, you can use linear regression to predict the price. The independent variables would be, for example, the age and location, and the dependent variable is the price. The weighted sum, which is the price, is the sum of the products of the independent variables and the weights as seen here. There's also a bias vector that sets the results when the independent variables are equal to 0. As the model is trained, the weights and bias will be adjusted so that the similarity between the prediction and the expected outcome, the human response, is within an acceptable threshold. In the next lesson, you'll start to implement some of the concepts in code. In this lesson, you'll begin to implement a neural network. To get started, you'll need to represent the inputs. Start off by implementing some operations on vectors, first with Python lists, and later using NumPy arrays. A vector has a direction and magnitude. You can represent a vector as an arrow in a graph. The magnitude of the vector is the length of the arrow. Here you can see 3 vectors, 2 for the weights of a neural network, and another for the input. It's obvious that weights 2 is more similar to the input than weights 1 by visualizing them. But how can you do this in Python? This is the purpose of the dot product. As the vectors are two-dimensional, you can compute the dot product of the input and weights 1 by first multiplying the first index of the input by the first index of weights 1, then multiply the second index of the input by the second index of weights 1, and finally, sum the products. Implementing this in Python is straightforward. Using Python lists for the vectors and manipulating the indices explicitly, you can calculate the dot product to be 2.1672. However, not all vectors are two-dimensional. As you work with higher dimensional structures, the code to compute the dot products gets more complex and slower as well. But NumPy ND arrays support dot products out of the box. Simply call the np.dot function and give it the input and weight vectors. As you can see, the result is the same. Compute the dot product of the input and weights 2, and the result is 4.1259. So how can you use this to determine the similarity? If the dot product is 0, the vectors are not similar at all. However, larger values mean that they are more similar. Since the dot product of the input and weights 2 is greater than that of the dot product and weights 1, weights 2 is more similar. The model you will train in this course will only have 2 outcomes, 0 or 1. This makes it a classification problem, as there is a fixed set of outcomes as the result. Suppose that you have this data set. The input vectors are what the neural network will use to make a prediction, and the target is what you want to predict. This, of course, is much simpler than a real-life network, which would work with text or image data. So far, you've seen the dot product and the sum, and both of these are linear operations. And if all the operations in the network are linear, adding more layers will yield nothing more than linear results. Therefore, you need to introduce nonlinear layers with activation functions. For example, the rectified linear unit, or ReLU function, is nonlinear in that it sets any negative value to 0. Essentially, it turns off all negative weights. The network you build will use the sigmoid activation function. This squashes the output between 0 and 1, and this is appropriate as the outputs in the dataset are 0 and 1. Thus, you'll assume any value less than or equal to 0.5 as 0, and all others as 1. This is the formula for the sigmoid function. You don't need to worry about proving it, but you will implement it here in code. That will be straightforward. The symbol e is a mathematical constant for Euler's number, and the function np.exp in NumPy will handle that. This diagram shows the different parts that you'll implement. Hexagons are functions, and the purple rectangles are outputs. You'll simply compute the dot product of the input and weights, add the bias, and then apply the sigmoid function to get a number between 0 and 1. And here's the code. First, express the input, weights, and bias as NumPy ND arrays. Then a function for the sigmoid activation function. Again, use np.exp for Euler's constant. The function makePrediction will implement the layers. The first layer takes the dot product of the input and the weight, then adds the bias. The second layer uses the sigmoid function, and the return value is the prediction. If you run the code, the prediction is 0.798. This is higher than 0.5, so assume it to be 1. Looking back at the training data, the expected outcome is 1. So this prediction was correct. Try it again with the second example. It yields a prediction of 0.871, which you'll assume to again be 1. But the expected outcome is 0. This prediction is incorrect. You'll need to adjust the weights to do better next time. But how much should each weight be modified? Watch the next lesson to find out. In this lesson, you'll complete the training loop by evaluating the error between the prediction and the target and adjusting the weights in the network layers. First, compute the error. The mechanism that computes the error is called a cost or loss function. For this course, you'll use the simple mean squared error, or MSE. This is done by taking the difference of the prediction and target and squaring it. And doing this in Python is not difficult. The error is just over 0.75. Notice that by squaring the error, it will eliminate all negative values. Also, it will emphasize the larger errors, and the network will learn more from those larger errors. Now you need to reduce the error. Consider only the weights for now and then tackle the bias later. The following graph shows two possible errors. They are on the graph of the quadratic function because you are squaring the error. The error value is on the y-axis. To reduce the error and make it closer to 0, you need to reduce the value of x for point A and you need to increase the value of x for point B. Like with vectors earlier, it's easy to see this in a graph, but how do you do it in Python? You'll use the derivative of the cost function to determine the direction to adjust the values. And the derivative is also called the gradient. And finally, gradient descent is the name of the algorithm used to adjust the weights. To keep things simple, you'll be able to use the power rule from calculus to compute the derivative of the cost function. The power rule says that for a formula in the form x to the n power, the derivative is n times x to the n minus 1 power. Thus the derivative of x squared is 2 times x. The error is computed by np.square and passing it the prediction minus the target. Therefore, consider the prediction minus the target to be a single variable. Thus the derivative of the cost function is 2 times the difference of the prediction and target. The Python code for this is simple, and you'll see that the result is 1.74. Thus, you should decrease the weights to reduce the error. Subtract the derivatives from the weights. You can do this easily using broadcasting with NumPy, and then call makePrediction with the new weights. This time the prediction is below 0.5. Also, the error is much smaller. It's almost 0. Does this mean the problem is solved? Not always. In this case, everything worked out. But what if the derivative were a larger value? The error could skip over the minimum and actually increase. Therefore, you will often use a fraction of the derivative to take smaller steps in reducing the error. This fraction is called the alpha parameter or learning rate. Smaller learning rates take smaller steps and vice versa. Often values for learning rates start off with 0.1, 0.01, or 0.001, and the only way to find the optimal value is experimentation. The new weights work great with the second input vector. Applying the weights to the first input vector will give you an incorrect prediction. When a model performs significantly better on the training data than it does on test data, the model is said to be overfitted. In other words, the model is too comfortable with the training data, but will perform poorly with new data. There are several techniques to avoid this. In the next lesson, you'll begin to implement one. To review, your network has two layers. For example, the error function is x squared, but x is the result of another function, the difference of the prediction and expected value, as seen in the previous lesson. When the input of one function is the result of another, it's called function composition. In the previous lesson, you saw how to use the derivative to reduce the error function. But since the error function composes other functions, you must use the chain rule to take the derivative and reduce the error. When using the chain rule, you take the partial derivative of each function and then multiply them. This isn't as complex as it might sound for the simple functions in this course. It's easier to see in a diagram. To take the derivative of the error function, you'll need partial derivatives. Take the partial derivative of the error with respect to the prediction, then take the partial derivative of the prediction with respect to the first layer, and finally the partial derivative of the first layer with respect to the weights. Then take all the partial derivatives and multiply them together. This product will give you the derivative of the error with respect to the weights. Perhaps you noticed that you are starting at the error and working backwards to the weights. This is called a backward pass, and the algorithm is called backpropagation. Here's how to update the bias. It's the same algorithm as for the weights, just different variables. So instead of taking the derivative of the error with respect to the weights, you take the derivative of the error with respect to the bias, as seen in this diagram. The error function is x squared, and the derivative, as you've seen, is 2x. For the next partial derivative, you'll take a step in reverse and compute the partial derivative of the prediction with respect to the layer. This is the derivative of the sigmoid function. For this course, just accept that it is the product of the sigmoid and the difference of 1 and the sigmoid. Finally, you can take the partial derivative of the layer with respect to the bias. If you multiply them, you'll get the derivative of the error with respect to the bias, and you'll use this value to update the bias to reduce the error. Here's what it looks like in Python. First, this function computes the derivative of the sigmoid function. The partial error of the derivative with respect to the prediction is 2x, but x is the difference of the prediction and the target. The derivative of the prediction with respect to the layer is the derivative of the sigmoid, which accepts the output of the layer. And the derivative of the layer with respect to the bias is the constant 1. Multiply them together for the derivative of the error with respect to the bias, and subtract that from the bias. And of course do the same with the weights and the derivative of the error with respect to the weights. You'll implement that in the next lesson as you write a class to build a neural network. Math class is over. In this lesson, you'll write a class to build a neural network and train a model. A lot of the code you've already seen, so we don't need to go through it line by line. The class is named neural network, and the initializer accepts the learning rate. Again, this is the value, which is the fraction of the derivative used to adjust the weights or bias. It's called a hyperparameter. The weights and bias are trainable parameters. In other words, they are variables that are updated as the model is trained. A hyperparameter is constant. It is set before training begins and does not change. It's kind of like a configuration value for the training process. Also in the initializer, the weights and bias are initialized. These are set to random values. Since the network in this course is so small, it probably won't have much of an effect which distribution you use, or even if the initial values are random. However, in a real-world scenario, this is standard practice. The code for the sigmoid and sigmoid derivative you've seen before and need no further discussion. The predict method computes the values for each layer and returns a prediction. Again, you've seen this code as well. The code to compute the gradients is a little different. Notice that when computing the partial derivative of the layer with respect to the weights, you must take the derivative of a dot product. To do this, take the derivative of the first vector and multiply it by the second. Then compute the product of the second vector and the derivative of the first. Add the two products and get the derivative of the dot product. The update parameters method is where you update the weights and the bias using the derivative, or gradients, returned by compute gradients. Each derivative is multiplied by the learning rate, then reduce the bias and weights to get better predictions. To use the neural network class, initialize it with a learning rate. Again, 0.1 is a common choice. Call the predict method with an input vector, and you'll get a prediction. But this network merely makes a prediction. It has not been trained. In the next lesson, you'll actually train a model. In this lesson, you will train a model. Again, when you train a model, you gradually adjust the weights and bias. Add a new method train to the neural network class. It takes a list of input vectors and corresponding targets. The final parameter is the number of training iterations. For each iteration, a random input vector will be selected. This vector will be used to compute the gradients and update the weights and bias. Every 100 iterations, it will make predictions for each of the input vectors and sum the errors, storing them in a list. And that list is returned. Let's try out the new train method. You can create a 2D NumPy array of input vectors and then a single vector of targets. Create a new instance of the neural network class and set the learning rate to 0.1. This time, instead of calling the predict method, call the train method. Give it the input vectors and targets and have it run for 10,000 iterations. This will return 100 cumulative errors that can then be graphed using Matplotlib. You'll see that while it's not a smooth curve, the error rate decreases rapidly and then settles into a fairly consistent range. Now that range is wider because of the dataset size. There isn't much for the network to sink its teeth into. Also, you're testing the dataset using the same data it was trained on, which can lead to overfitting. A real-world deep neural network would be designed to work with much larger datasets, and also it would have many more layers. As layers and activation functions are added to the network, it increases the accuracy of the predictions generated from the trained model. Neural networks are best suited for problems with complex data, such as object detection. In the last lesson of this course, let's review what you've learned. In this course, you learned the foundations of deep learning and neural networks. You also built a simple neural network from scratch in Python and used it to train a model. Along the way, you learned about the differences between deep learning and machine learning, and you saw how to represent data with NumPy. You learned about activation functions and their task in a neural network. You implemented the backpropagation algorithm that updates the weights and bias in the network to increase the accuracy of predictions as the model is trained. And you learned how to train the network and use the trained model to make predictions on new data. Now, it's theoretically possible to implement a production neural network using NumPy, but it's not practical. For production neural networks, you can rely upon frameworks such as TensorFlow, Keras, and PyTorch. These take care of a lot of the boilerplate code. You only have to worry about the part that relates to your unique data, the design of the layers. For more information, you can check out these resources on RealPython. Note that I have also created a course based on the resource Practical Text Classification with Python and Keras. Thank you for watching this course. I hope you found it helpful. If you would like to continue the conversation, please leave a comment, or you might like to join the discussion forums on realpython.com.